Hello everyone, I am Bernardo Magri and I'm going to present our paper Cryptographic Reverse Firewalls for Interactive Proof Systems. This is a joint work with Chaya, Ganesh and Daniele Venturi. So interactive proofs are two-party protocols that are run between a prover and a verifier, and the objective is for the prover to convince the verifier that public statement X is in some language L. For the prover to be able to do this, we allow him to have a witness, which is a witness of the fact that X is indeed in the language. In the case X is a true statement, and in this case the verifier must accept. And in case X is not in the language, the prover shouldn't be able to convince the verifier of the fact that X is in the language, or shouldn't be able to fool the verifier. So for interactive proofs to be useful, we usually require some properties. So the most basic is completeness, that just says that whenever this pair of statement and witness is in some relation, it's a valid pair, then the prover will always convince the verifier of this fact. And the soundness, which is a security property for the verifier, just says that whenever X is not in the language, no efficient prover can actually trick the verifier into accepting a false statement. And we usually also consider zero knowledge, that just says that the proof, the interaction, the transcript of the protocol does not leak any information of the witness of the prover to the verifier. So this is a property for the prover himself. So the big question that we ask in this work is, can we design these interactive proof systems to be secure even when one of the honest parties in the protocol has its machine compromised? So you still have one of the two parties malicious, and the honest party is also compromised now. So what can we do like in such a case? So it turns out that in general, there's nothing much you can do actually, because if you look at closely, like a honest but compromised prover, compromised in the sense that the code of the algorithm that the prover runs could be arbitrarily replaced by something else. So in this case, the prover could simply just output the witness to the outside world if the objective is to leak the secret of the prover. And in this case, it's impossible to get zero knowledge because the witness would just be output. And an honest but compromised verifier could also be rewired to just accept all statements, and then you cannot get soundness in this case because it just accepts even false statements. But if we add some extra assumptions, we can actually have some positive results out of this. So we can actually build some secure IPSs, and we use this cryptographic reverse firewall model, which was introduced at Eurocrypt 2015 by Mironov and Stephens Davidovits. So what this model proposes is that there is something that is called a reverse firewall, which can be seen as a piece of hardware or software. It's something that sits between one of the parties and the outside world. So here in this image we can see a reverse firewall being deployed on the side of a compromised prover, and the firewall basically will just sanitize all the information that the prover tries to send to the outside world, the compromised prover. And the firewall doesn't need to exchange any secrets with the prover. So in particular, the prover does not need to trust the firewall to send any secrets to it. The only assumption of the firewall here is that the firewall cannot be compromised itself. So the code that the firewall is running cannot be compromised. Otherwise, we're back to the question before, that where everything is compromised. So a little on related work before we start talking about the contributions is that in in Eurocrypt 15, where the Mironov and Stephens Davidovich, they introduced this model, they actually show reverse firewalls for arbitrary two-party computation protocols. So in particular, an IPS, as we said before, is a two-party computation protocol. So the protocols that they propose, in some sense, already solves this problem. However, their solution are not ideal because it requires, one of the solutions requires to recompile the IPS protocol. Basically, all the communication of the parties takes place in the encrypted domain. So before you actually deploy the firewall, the protocol needs to be redeployed. So it's not transparent as you have the protocol running and you just put the firewall between the parties and everything works. And the second solution that involves garbled circuits where they give a firewall for a private function evaluation, and this is also highly inefficient for our case. And moreover, we also provide security definitions that are tailor-made for IPS, whereas in their case, since they are dealing with arbitrary protocols, they need arbitrary security definitions that doesn't always translate in the best way to IPS. So we also propose some new security definitions. And in the paper, we also discuss a bit the relation with all these other areas of subversion, cryptography, algorithm substitution attacks, and so on, which is all related in some sense. So let's talk a bit about Sigma protocols now, which is a special type of interactive proof systems, which are just 3 rounds where the prover sends the first message and the verifier sends a random challenge, and then the prover sends a response. So this is very efficient, and it's used in cryptography for many different applications, from identification protocols, blind signatures, electronic voting, and general multi-party computation. And the properties that the Sigma protocol gives us is special soundness, which is a stronger form of soundness, which just says that if you take 2 transcripts of a run of the protocol for the same witness but with different first messages from the prover, you can actually extract the witness from this. So this basically just says that in order to convince a verifier, the prover must know the witness. And for the prover, this gives the property of honest verifier zero knowledge. So this just gives the property of zero knowledge when the verifier is honest but curious. So essentially, the verifier just follows the protocol but tries to learn some more information, but always following the protocol. So these are the communication. So prover sends alpha, receives beta, and sends gamma. So now developing like reverse firewalls for this type of IPS, for example, what we want to achieve here is transparent reverse firewalls, in the sense that you don't need to recompile the protocol or redeploy the protocol. You just have the protocol running and just insert the firewall and everything should work. In particular, the firewall, when the party is not compromised, the firewall should not destroy the functionality of the protocol. So it should work even when there's no compromised party. So here we have just the Sigma protocol with the prover and verifier that produces a transcript tau. And in this other side, we have what we call a sanitized Sigma protocol, which is when the one party, in this case the prover, is honest but compromised, and we compose the prover with the firewall, and we get this sanitized transcript here, where the messages were changed by the firewall. So let's talk about some possibilities and impossibilities that we show for reverse firewalls in this setting. So first, when we talk about preservation of some property, this means that, as we showed before, the original IPS and then the sanitized IPS. So if the original IPS had this property and the sanitized also have this property, we just say that the property was preserved. So let's first look at the case for the prover. So we showed that we can preserve completeness. We showed that we can weakly preserve zero knowledge for the prover. And here we should say that all the weak variants of these properties are for functionality maintaining parties. And functionality maintaining parties are, for example, the prover is when the prover has a valid statement and witness pair, it still convinces the verifier. So it still needs to produce a valid transcript of the protocol. So in particular, this intuitively models some kind of compromise that is undetectable from the outside. So if the prover just outputs the witness, as we said before, one can argue that this is easily seen to be compromised. So the adversary compromising the system would like for the user to still use the system such that he doesn't note that anything is wrong with the system. So we have this this notion of weak variants for this type of parties that preserve the functionality or gives a kind of undetectable attack. So we have the same result for witness indistinguishability, which is just a weak zero knowledge. So basically this just says that if you have two different witnesses for the statement, the verifier cannot tell which witness the prover actually used to produce the proof. And here again, we cannot have the strong variant because the strong variant is for arbitrary compromised provers. And again, the prover can just output the witness. So you can never get a strong variant, but only for the weak, for the undetectable attacks. An exfiltration resistance is a property that just tells that if you take the transcript of a sanitized protocol when the prover is honest, and the sanitized protocol when the prover is compromised, they are indistinguishable. So this just tells you that even when if you sanitize the protocol and even when the party is compromised, the distribution of the transcripts are identical or indistinguishable, at the very least, computationally indistinguishable. So this just intuitively says that no information can be extracted from this transcript that couldn't be extracted when the prover was honest, for example. Now for the side of the verifier, things are a bit worse, because in this general sense, as we consider for the prover, we can actually not get any security for the verifier, any security preservation. And the reason is that the verifier produces an output, and the output is not touched by the firewall. So the verifier will receive the messages, and the firewall can sanitize the messages, but the verifier needs to produce the output eventually. So in the paper we actually show like a weaker form of compromise, a partial compromise, where some parts of the algorithm can be compromised and others not, and we do show some positive results in that case. But in this talk we'll focus on the prover side. So as a warm-up, let's look at the Schnorr protocol for proving knowledge of discrete logarithm. So we have here this public statement, G and X, and the prover wants to convince the verifier that he knows some witness W such that G to the W is X. So first he generates some random A, computes G to the A and sends this to the verifier. That computes a random challenge beta, sends it back, and then the prover computes the response gamma, which is of this form, and sends gamma to the verifier that needs to check if this equality is true. And if this equality is true, he can accept the proof as valid. So now how do we build a firewall in this case if we assume that the prover now is compromised? First, the prover will act exactly the same because, as we said, the firewalls needs to be transparent. So the prover and the verifier won't change in anything what they do. So the only thing is that all the messages sent by the prover in this case will be intercepted by the reverse firewall, and the reverse firewall will sanitize the messages. So in this case, the firewall will receive alpha and produce this alpha hat, which is of this form, just multiplying by some random group element, and sends alpha hat to the verifier. So now for the verifier, he's just receiving alpha hat. It's just the same as the prover had sent a different group element in this case. So it is completely transparent for them. So now the challenger just sends beta again. The firewall just relays to the prover that will compute gamma, and now the firewall needs to adjust this gamma hat to match the first message alpha hat that was sent. And this is sent to the verifier that will now check this equality here, which is a bit different. And this weakly preserves zero knowledge. We show this in the paper. One of the many instances of Sigma protocols. So here, if you note, this G to the A times G to the sigma, this is actually just alpha hat, which is the same as before, as we see here. So another class of Sigma protocols within Sigma protocols is what we call the malleable protocols, which are protocols that admit this operation that we just did. Basically, that admit that the first prover's message alpha can be re-randomized into some identically distributed alpha prime or alpha hat, and then the response message gamma can also be balanced to match the different message alpha prime in this case, and that the response message gamma is unique. Once you fix some first message and the challenge, you have only one possible response for gamma, and this is required because if you had different possible responses for gamma, the prover could for instance, try to leak information about the witness just by picking different choices of gamma, for example, and using it as a subliminal channel to leak information. And we show that many examples of Sigma protocols are actually malleable. For example, the Mauter's unifying protocol, which already covers a huge class of Sigma protocols, in particular all this cited here. So let's now look at how to build a reverse firewall for this malleable Sigma protocols, which is just an abstraction of what we did before with Schnorr. So here we just have a generic algorithm producing a first message that is intercepted by the firewall, that it will just mull this first message alpha into some alpha hat that goes to the verifier that sends the challenge, and now the prover produces his response, and the response is intercepted by the firewall that will balance gamma to some gamma hat based on this random coin sigma that was sampled before to produce alpha hat, and this is sent to the verifier that will perform its normal check. So let's talk a bit about why the the proof of honest verifiable zero knowledge preservation holds. So we have here the Sigma protocol, and we have the prover and the verifier communicating, and this produces a transcript tau with all the messages exchanged. And this is the original Sigma protocol. So now if you look at the sanitized one, where the prover is compromised and the messages are re-randomized by the firewall, we have this tau hat with these messages exchanged. So what we want to show is that when we fix any pair of valid statement and witness in the relation in a functionality maintaining p tilde, any functionality maintaining compromise prover, and we want to show that the distribution of these two transcripts is identical. So in particular, we look at each message in this transcript. For example, the first message that the prover sends is alpha, and then the firewall re-randomizes to alpha hat. And by the uniformity property of malleable Sigma protocols, we show that the distribution is identical. So exactly how we showed for the example for Schnorr in that case was multiplying by a random group element. So here the challenge beta is still uniform because the verifier is following the protocol, so it's honest but curious. So this we get for free. And the last message that the firewall balances to match the first message alpha hat that was changed, and we get that this unique response of the Malleable Sigma protocol. So there is a single gamma hat that for an alpha hat and a beta that will produce the valid verification. So all this gives us that the distribution of the transcripts is identical, and therefore, since the initial IPS, the Sigma protocol, is honest, verifiable, zero knowledge, we get that the sanitized protocol preserves this property. So concluding, we also build extensions for all this. So we do a full zero knowledge protocols, but in this case we require some malleable commitments in the first messages where the verifier needs to commit to the challenge beta in order to full zero knowledge to hold, and this we show that we need some malleable commitments. For example, we show that Pedersen commitment has this the properties that we need, and we also build firewalls for compound statements like and or composition, where you want to prove more than one statement at the same time. And as an open problem, we leave how to build a reverse firewall for the or composition when the inputs of the parties is delayed. So that's all that I wanted to say, and thank you all for your time.